Hi class, today we're going to talk about section 3.5, which is on complex zeros and the fundamental theorem of algebra, which I'm going to abbreviate like this a lot. All right, so first we want to talk about the complex number system. So in the complex number system, which we will denote as a fancy C, an nth degree So what we're saying here is that an nth degree polynomial with the complex number system, it will have exactly n zeros. And we're going to introduce this thing called multiplicity. So that means in your factored form, you'll have like x minus 3 squared. That means that our polynomial will have a 0 of 3 multiplicity 2. And I'll explain that more as we go on. All right, so first, I'm going to state the fundamental theorem of algebra. So, as you can imagine, since it has the word fundamental in it, this is a very important theorem for us. And what it says is that every polynomial p of x equaling a n x to the n all the way down to a1x plus a naught with n greater than or equal to 1 and our a n not equal to 0 with complex coefficients remember, a real number being like 6, that's still a complex coefficient. It just has a 0 imaginary part. So with complex coefficients, a, c1, c2, all the way down to cn, such that, I'm so sorry, okay. This is actually a theorem that comes later. I just glanced at the wrong part of my page. So sorry about that. Okay, so with complex coefficients has at least one complex zero. At least one complex zero. That's the most important part. And so we can remember that a equals a plus I0 when a is a real number. So this is a complex number. So that's an important thing to remember. So then for our next theorem, which I glanced at earlier, this is called the complete factoration theorem. Factorization theorem. Okay, so here we have if p of x is a polynomial of, whoops, that's not how you spell degree, of degree n, then there exists complex numbers a, c1, c2, all the way to cn, such that p of x equals a x minus c1, x minus c2, all the way to x minus cn, with our a term not 0. Okay, this means that any polynomial when we're including complex numbers, it can be completely factored, which is a really nice thing to know because it will let us write all of our zeros down. All right, so the big idea with this is that with the fundamental theorem of algebra, which I will often write as FTA, our polynomial P has at least one zero. Let's call it C1. Then we can write P of x equals x minus C1 times some Q1 of x, where Q1 is a degree n minus 1 polynomial. Well, then we can apply the fundamental theorem of algebra again. And then we get our P of x equals x minus C1, and then we'll have our new zero we'll call C2, x minus C2, and we'll call our next one Q2, or yeah, Q2. So if we just continue like this, eventually we'll get a polynomial of degree 1. And we'll call that polynomial A. So then we can write P of x equals, and we're going to just bring the A to the front, A of x minus C1, x minus C2, all the way down to our x minus Cn. Well, this is what we wanted. This matches what we said at the beginning of our complete factoration theorem. It matches perfectly with this. All right, so moving on from here, my pages on my notes stuck together. There we go. We're gonna do an example where we factor a polynomial completely. So we're gonna if we have P of x equals x cubed minus 2x squared plus x minus 2. We're going to group like terms because you can see here these look very similar. So we're able to rewrite this as x squared times x minus 2 plus x minus 2. And then we can pull out an x squared plus 1 from this term by grouping. So we're able to rewrite like this by factoring out our x minus 2 term. And then we know here, this is 0 when x equals plus or minus I. And this is 0 when x equals 2. So now we know what our zeros are. So we can completely write it down as x minus I, x plus I, and x minus 2. And there we go. That's our completely factored form. And now we can do another example. And this is x cubed minus 2x plus 4. So if we use the rational zero theorem, then the possible factors possible factors of 4 are plus or minus 1, plus or minus 2, and a plus or minus 4. So now we need to test for zeros. So we can see, I'm just going to let you guys know that -2 is a 0. You guys would need to check on your homework until you found one. But so if we just start with a -2, then using synthetic division, we get -2, and then we'll write the exponents out. We get a 1, a 0, a -2, and a 4. Bring down our 1, we multiply, we add, we multiply, we add, we multiply, we add. And so this checks out. We get a remainder of 0. So this means that -2 is indeed a 0 of p. So then we have our new polynomial, so we can rewrite p as x plus 2 and x squared minus 2x plus 2. This is from our synthetic division. And then here, we can just use the quadratic formula. So remember, that will be -b plus or minus the square root of b squared minus 4ac all over 2a. Just for a reminder, in case it's been a while since you've seen it. So if we were to do this, we would get a 2 plus or minus the square root of 4 minus 4 times 1 times 2, all over 2 times 1. Well, then this simplifies down into 2 plus or minus the square root of -4 over 2, which if we simplify, this becomes 1 plus or minus I. So our zeros are -2, 1 plus I, and 1 minus I. So our factored p x plus 2 times x minus 1 plus I times x minus 1 minus I. And then we can simplify that a little bit if we would like. And we get an x minus 1 minus I and an x minus 1 plus I. So there we go. There's our factored form. Okay, and then moving on from here, we're going to talk about zeros and their multiplicities. So first we're going to define multiplicity. So if the factor x minus c appears k times in the complete factorization, then we say that is a 0 of p with multiplicity k. So multiplicity really is just a fancy way of saying that this 0 appears this many times. So for example, for p of x equaling x minus 1 cubed x plus 2 squared, and x plus 3 to the 5th. So that's a completely factored polynomial. It has zeros, 1, mult 3, and I'll usually write multiplicity just as mult because it's a lot faster and easier for everyone. All right. And then it has -2, mult 2, and -3, mult 5. So yeah, I'm totally fine on the homework if you guys just want to write it as mult instead of fully writing out multiplicity. All right, and then a good fact to know is every polynomial of degree n greater than or equal to 0 has exactly n zeros, provided that the zeros of multiplicity k are counted k times. So there's a secret P in there. Yes, so as long as we count the multiplicities the same number of times, we'll get exactly n zeros. So for an example, if we were to factor 2x to the 5th plus 36x cubed plus 162x and find all 5 zeros. So first we're going to notice our common factor. Of 2x. So if we pull that out, we have a 2x, x to the 4th plus 18x squared plus 81. And then we'll notice that this will become x squared plus 9 squared, because 9 squared is 81 and 9 plus 9 is 18. So this has a 0, 0. And this polynomial here has zeros 3i and -3i, each with multiplicity 2. Because this gets factored into 2x, x minus 3i, x plus 3i, all of that squared. All right. My pages still are stuck together. All right. Okay, and now we're going to do another example. We're going to find a polynomial. So now we're going to construct a polynomial that has these zeros and that when you put 3, you get 25 out. So P is going to equal A times x minus I, x plus I, x minus 2, and x plus 2. So if we were to multiply these out, we'd get an A, x squared plus 1, and an x squared minus 4. And then if we multiply out again, we get an A, x to the 4th minus 3x squared minus 4. So now we're going to plug in 3 for our x. There's a little secret, little x up here. So then P of x, P of 3. This equals A times 3 to the 4th minus 3 3 squared minus 4. And this will equal a times, if you do this math out quickly, you will see that this is 25. I'm sorry, that this is 50. And so but we also know up here that p cubed needs to equal 25. So this means that our a has to equal 1/2, because 1/2 times 50 equals 25. So then we can write p of x equals 1/2 x to the 4th minus 3/2 x squared minus 2. Also, a note on homework, if y'all could box your answers, that would be really helpful for me when grading. Just like this. All right. So now we're going to give you a helpful fact. If a polynomial p has real coefficients, the real part is important, and the complex number z is a 0 of p, then the complex conjugate z bar is also a 0 of p. And here are some examples of when this happened. So if we have x squared plus 4, well, this gets factored into x minus 2i, x plus 2i. And so our zeros are plus or minus 2i. And also, if we had x squared minus 2x plus 2, well, this gets factored into x minus 1 minus I, x minus 1 plus I. So our zeros are 1 plus or minus I. So remember that a complex conjugate, if z equals a plus ib, z bar equals a minus ib. All right. So now we're going to talk about one last topic for this video. Sorry, it's a little bit of a longer one, and it's going to be linear and quadratic factors. So a quadratic polynomial with no real zeros is called irreducible over the real numbers. So, a quadratic irreducible Okay, so why this is important is because every polynomial with real coefficients they can be factored So every polynomial with real coefficients, they can be factored into a product of linear and irreducible quadratic factors with real coefficients. So this means the linear are our zero terms. So that's something usually of the form, let me kind of make a note, of the form x plus or minus c. And then the irreducible parts are when the zeros would be complex, so we're keeping everything with real numbers. Example of that would be x squared plus 1, because the zeros of this are I and negative I. All right, so the big idea behind this fact, is that if we have our c equals a plus ib, so c is a complex number, then x minus c and x minus c conjugate, this equals x minus a minus ab and x minus a plus ib, which equals x minus a minus ib, x minus a plus ib, which we can separate, and we get an x minus a squared minus an ib squared. But remember that I squared is negative 1, and a negative 1 times a negative is positive. So then we get x squared minus 2ax plus a squared plus b squared. And then this becomes x squared minus 2ax plus an a squared plus b squared. This is a quadratic with real coefficients. So as long as our polynomial has real coefficients, it can be factored into something that stays with real coefficients. So an example of this is if we factor x to the fourth plus 2x squared minus 8 into irreducible factors. So if we have our p of x equals x to the fourth plus 2x squared minus 8, we are able to factor this as x squared minus 2, x squared plus 4. And then here we can factor that, whoops, don't know what happened there, into x minus the square root of 2, x plus the square root of 2. And notice, we're just saying real coefficients. They don't have to be rational, which is why our plus and minus square root of 2 is all right here. But then we're going to keep x squared plus 4, because this has only complex zeros. Plus or minus 2i. So this would be our complete form, and then we would be done. Sorry that this was a longer video, but it was some very important topics. So thank you for listening, and I will see y'all with the next lecture.